show of hands, how many of you have recently deployed a digital twin? Okay, well, congratulations on becoming digital parents. For the rest of you, the single child parenting class is next door. You're in the wrong place. Okay. So with that said, I want to maybe make this more for storytelling, try to keep it lively and get some interaction. So when we talk about process optimization using digital twins or predictive analytics, really what are we talking about? We're talking about two things. Talk about first making predictions, okay? And then just making predictions is not really enough. You really want to predict an outcome because making random predictions is not very useful. So Tyler and I would like to take you through a journey of one of our recent projects, and hopefully you'll find that beneficial for yourselves. So what have we done? It's really been 4 steps. We first built a process digital twin. Okay, so we're in the tissue making part of Kimberly-Clark, so our process is making tissue. We used a platform from BrainCube. There's a number of reasons we preferred that, but that was the architecture we built it on. And the data was coming from our historian, OSIPI, plant apps. And there was also a need to pull data in from our Rockwell DCS system. We then used the digital twin to do 2 things. We used it first to identify what variables or what data was needed to be used in the model. And then we went back and we confirmed that the tags that we had selected made sense. After that, we developed and deployed machine learning models. And for our process, there's really 4 key quality metrics of interest. So we ended up modeling all 4, but today we're going to present 1. And so we built a model to predict, in our case, it was basis weight. That was coded in Python and deployed in a BrainCube managed server. Now, one key element was that the model was designed to auto-refresh because in our world, we're talking about control systems, right? It's like a PID loop. You don't want to go and touch a PID loop tuning every 3 months or 6 months. You want to tune it, you want to walk away and forget about it. So we designed the model to auto-refresh and auto-deploy, so it sort of becomes maintenance-free. And then lastly, we came back and reused the digital twin to specifically do 2 things. We used the twin to test the model for stability and to help troubleshoot when we found that the model was unstable under certain conditions. And then we also used the model to optimize the accuracy of the prediction. So hopefully you get an idea of how we sort of used the digital twin technology and capability to really then deploy a machine learning model for our process optimization. So I know that there's a lot talked about what digital twins are. I want to help clarify the air, okay? And I want to explain when is a twin not really a twin. So the term digital twin has got nothing to do with technology. It was a phrase coined in 2011 by Angela Merkel, and she was giving a speech in Germany. We took it as gospel and adopted it like it came from some deep technical background. Not true. Okay. So pre-industry 4.0, back to 2011, we've always been doing digital twins in the control world. Just think about it. We just called it different things. We talked about emulation, simulation, observers, classical control theory. We would have adaptive control using observers. These are all elements that today are passé. Today, if it's not a digital twin, you have nothing. Okay, so when we talk about digital twins, really a lot of people talk about 4 things, and I've listed them there. System, process, product, and part. These are just different ways of trying to classify the functional purpose of the digital twin that you may choose to deploy. Now, one thing to keep in mind, that the objective hasn't changed from the 1980s or 90s or all the way through today. The objective is the same, but the approach is very different, or in some cases can be different, doesn't have to be. So what do I mean by that? So back in the old days, we would write algorithmic-based transfer functions, or the emulation or simulation would be physics-based, math-based. It would be using things like loop-back techniques to sort of make the feedback look like what you want, right? What do we do today? Today, it's data science-based, it's data analytics. The objective is the same, but the techniques used have changed. One would argue that maybe they've become less engineering-focused and more data science-focused. That's not a bad thing. But I also want you to be very clear, at least this is my perspective, or our perspective, Tyra's and mine, right? What makes a digital twin? There's 4 key things. And in my perspective, if it fails to meet all 4 of those, you don't have a twin. So what's the first thing? The predictions have got to be verifiable. Okay? As engineers, which I believe most of us are, we've got to be able to duplicate results. We've got to be able to go back and say, yes, let me show you here. I can demonstrate, I can verify. Then, just getting a prediction that's been verified is no good if you can't take action on it. So the prediction has got to be actionable. Now, actionable may mean different things to different people, but in most cases, it brings the assumption that you have sufficient time to actually do something. If a prediction is too late for you to actually act upon it, even if it's accurate, it's really not very actionable. So you need both. You need verifiable, you need actionable. And then you need some level of agreement between you and whoever you're working for, right? Usually process folks or business folks, on the level of stability and the level of accuracy. You're never going to get a perfect digital twin. So you're going to have to sort of agree on what level of stability is considered acceptable, that's your threshold, and what level of accuracy is considered acceptable. If you can meet all 4, you do have a digital twin. Otherwise, you may have a distant cousin. So coming back to, helping you understand what are the different purposes of a twin. And I'll say one thing. If I had gone back and redrawn that slide, I would have probably offset those circles, so they wouldn't all live one within the other. So my bad on that. But the point I want to make is a twin is designed for a specific purpose. You can't use it for a purpose that it was not designed for. Okay? And yes, you can have twins that have larger scope and therefore can be used for more things. But in this particular example, if I were to have built a twin for parts, so that's a reliability play, I really can't take a model or a twin designed for reliability and use it for process optimization. At that point, it's not a twin in the process world. Okay? And so you can see that part of the challenge when you decide that you're going to go make or build a digital twin is to define the scope, because things can get expensive very quickly, can get overcomplicated. And don't forget that once you become digital parents, you have to feed that twin for 18 years. You got to nurture it, you got to keep it alive, you got to keep it calibrated, right? Otherwise, it's going to just wither and die. And so don't forget that you want to look at a digital twin through the life cycle of not only just the twin, but your entire machine. The next thing I want to do is I want to demystify data. Now, data is something that's been much talked about since Monday morning. Everything protecting it, collecting it, moving it, dissecting it. I'm going to bring it down to very simple terms. And I'm going to probably ruffle a few feathers because I stand on the right-hand side of that chart, and many of my colleagues are on the left-hand side. So what am I talking about? There's 2 different perspectives on how data is needed. And part of the goal is really to bring the 2 together, okay? So while I make light of it, it is not about being separate, it's about bringing the 2 approaches together so you have the right approach. So on the left side is what I call the data science approach. And what I mean by that is data scientists love extensive historical data. More is better. Okay, you can never have enough. And there's a tendency, and I generalize, so forgive me for that, there's a tendency to value quantity over diversity. When you talk about model evaluation with data scientists, they use statistical metrics and everything is randomized. Okay. And lastly, model stability is often ignored. You talk about R-square, you talk about MAPE, percentage errors, and everything in a random perspective. On the right-hand side is what I call the digital manufacturing approach, or maybe more of an engineering-based approach, where I would say that limited data is often better. And the reason I say that is your footprint is never in steady state. You're always rebuilding machinery, you're doing preventive maintenance, you're changing consumables. So your capability is never consistent. And if you go too far back, it's like trying to predict what an 18-year-old is going to want to eat if you go back to when he was 6 years old. It's like the further back you now go, the more your data is actually going to hurt your prediction. And so there's an element of that in the real world when you're talking about real equipment. And diversity is often more important than quantity, because diversity gives you really what you probably are looking for in the near term. When it comes to model evaluation, yes, you do need to do some random testing, no doubt about that. But what I often find more important is time series testing, because the value of time series is you can look at the predictions and you can now go and pull data from your historian and you can match things up. And you can sit down with a process expert or a subject matter expert and you can try to figure out why things don't look right or confirm that they do look right. Random evaluation by itself misses that element. And lastly, I would say stability is paramount. I mean, I would get fired if I went and put an ML model on a machine and caused an upset condition, right? There is no room for forgiveness. You bring in new technology, it better work the first time, or you may not get a second time in your career. So, tissue machines are large, they're expensive, and you don't want to create an upset condition by putting in some machine learning AI digital model. So just to belabor this data analogy a little bit more, if I were to say, here's a dinner analogy. If the objective was to host a dinner, where the objective was to have the least leftover food, okay, what would the two different approaches be? Well, the data science approach would be, I want to know what everybody ate for the last 6 months, or maybe the last 2 years, what they ate for breakfast, lunch, dinner, what they ate on Monday, Tuesday, Wednesday by day of week, and then I can go make a prediction. Maybe the digital manufacturing approach is like, grandpa recently gave up red meat because of high cholesterol, and grandma is now diabetic, and one of the grandkids turned vegan. That may actually influence your menu and your leftovers more than what was consumed in the past 6 months or 2 years. So my point is, value diversity, certainly value quantity. And keep in mind that the more quantitative data you use, the less diverse data you retain. Because if you just looked at the last 2 weeks, you probably would capture the vegan diet, the high cholesterol diet, and the diabetic diet. But you go back 2 years, and that little bit of data gets crowded out, and you lose the diversity. So things to keep in mind as you build digital models, as you build digital twins, is what data helps and what doesn't. The last thing I want to point out before I hand it over to Tyler is, so this is a model that we have deployed. I use model and digital twin interchangeably. So what have we done is we are predicting basis weight, which is one of the key metrics, the quality metrics for our process. The blue diamonds are lab measurements. That's a control variable. That's what we're trying to predict. Now, initially, we used a data science approach, which was the green dots. And we are predicting at like a minute or, we're doing it faster than the lab measurement. So you have a lot more green dots. And you can see, hopefully, even from the back, that there are periods when the green line is pretty good. And then there are periods where the green dots are like a little cloud cluster, right? And the reason I want to show this slide is that's a watch out. So what happened in this case is an over-reliance on data that is simply correlational. Okay, correlational data is all well and good, but it can bite you because sometimes correlation is simply a correlation. It's like ice cream sales go up when shark bites go up in Australia. There is no actual cause and effect, it's just a correlation. So be careful when you use variables and assume that there is cause and effect. What we then did is we built a physics-based model, which is the dark brown reddish line, using actual equations and doing the math. And certainly the physics-based model is stable. A lot more effort. The data science approach is much simpler, easier. But the point I want to make then is you don't have to be single dimension when you build a digital twin. It's okay to consider a hybrid model where you may use a combination of physics or the old-fashioned algorithmic-based approaches and improved with digital data science approaches. So what we ended up actually doing, and I don't have a slide to show, we ended up using the physics-based model to predict the base value. And then we used a data science approach to predict the error between the physics model and the lab measurements, so that I limited the reliance on data science and I never go unstable. And I can still take advantage of simple correlational relationships to improve performance while maintaining stability.
Okay, thanks Vivek for that great introduction. Hi, I'm Tyler, working with Vivek and Kimberly-Clark on a lot of these AI programs. So I'm just going to explain a little bit about what BrainCube is and how Kimberly-Clark has specifically used it in the development of a lot of our digital twins. So BrainCube is just a platform we've used to kind of bring together everything we've needed to develop all of these digital twins and these modelings. It just brings it all together in one convenient kind of package. And what sets BrainCube apart is it brings together a lot of these different tools that we've been able to use to import data, push data, manipulate data, and analyze data. And we use these 4 tools specifically in the development of our specific models. So first of all, we have the BrainCube API, which is basically a way of interacting with the BrainCube cloud. And BrainCube provides us with an IoT server as well as a cloud platform that enables us to perform all of these different calculations and allows us to run custom Python models to implement all of these machine learning algorithms. So the BrainCube API allows us to pull directly from the cloud to each of our different IoT offline models, as well as some of our online models that we have. So what we've also done is on the model runner side of things, that is a tool that enables us to basically run custom Python models inside of the IoT server side of things. So inside of the BrainCube platform, we've been able to run a lot of these different models. And lastly, the BrainCube transfer nodes and the PyWeb API nodes are just 2 different tools that enable us to basically just push and pull data from the cloud and from our PyWeb API historians. So, and to go into a little bit more detail into what the model actually is, all those 4 tools just brings all the data together. We're then able to kind of implement in this diagram here. So we have about 4 models running simultaneously, which we're able to use with our different 4 quality variables. To go into the specifics of one, at least, we use 3 different linear regression models classified by grade to then classify the baseline model, as Vivek said. And then we use in this case, bagging regression model to predict the offset from this baseline prediction. And this kind of hybrid approach has given us a lot of benefits, which I'll go into briefly. So those who don't know what a bagging regressor model is, it's kind of a way of aggregating multiple different types of machine learning algorithms. So SVR, linear regression, k-neighbors, to name a few. and bring it all into one kind of prediction, which has numerous benefits for stability, which, as Vivek mentioned earlier, is our main concern, is just getting the most stable prediction, making sure these models are reliable over time. Once we actually generate a prediction, we're able to then push the data to our PLCs for closed loop control. But we can also we can also send those predictions directly to the cloud for visualization, future data analytics, and all sorts of BrainCube specialized cloud computing tools. And to go into a little bit of detail as to what those look like, we have this tag correlation analysis. So BrainCube wasn't just helpful for deploying these models, it was actually also helpful in the direct development of a lot of these models. So once we had all this data aggregated, this is about 4,000 data points that we pull from our machines. This is pulled once per minute, so an extremely large amount of data. So how do we determine which data points to use in our models? Well, BrainCube basically gives us an analysis tool that allows us to basically, in this case, for basis weight, we're able to show a graph, and in that graph, a step change inside of the basis weight calculation. And with this analysis tool, it was able to try to find a correlation between that step change and the step changes of the different models around that same time region, or sorry, the different tags in that same time region. So what this tells us is, and you can see it highlighted in green here, that these are potential correlated variables to basis weight. And using this kind of method, we're able to, with minimal help from process engineers and data scientists, develop a model and the input tag variables necessary to create a lot of these models. Whereas before, we would have had to rely very heavily on the expertise of process engineers. So this is just a way of kind of simplifying the process and expediting a lot of these model building. So it's not just for actually creating the models. We've also actually used it for the validation of some of these models. So what we've done here has been using the same analysis tools. We had this is our basis weight model, which had the same sort of rainfall scattering cloud issue that Vivek showed earlier. But in this case, this was in our actual prediction model. So what we had initially expected was there was probably some input variable that we had used in the model that was giving some weird, unexpected data, which was causing that unexpected variation in the actual prediction. So what BrainCube was able to do for us was we were able to highlight a region in red here and indicate that this is a problematic data set and show what it should be in the green there. And what BrainCube was able to do was run an analysis and push and basically identify the top 3 or 4 contributing variables. And the third and fourth one here, you can see is both refining. And after looking through the code at the model inputs, as well as discussions with our process engineers, we actually made a discovery. We made a pretty big mistake in that we had accidentally included these refining variables in the wrong model. It should not have existed inside of this basis weight model, and just, what would have taken hours of work going through all 4,000 of these different data tags that we use on our machine, we were able to do in just a few clicks. It was able to directly spit out as the third and fourth highest contributing variable this exact issue. So altogether, this was able to generate a whole bunch of different models, and with our ability to run predictions about once every minute, develop these models about once every 20 minutes on just 2 weeks of data, as Vivek was saying earlier, oftentimes less is more. And being able to generate a lot of these very high quality predictions using just a really minimal sample size is quite extraordinary. So hopefully this talk helped you better understand how we've used a digital twin in our application, and I'll hand it off to the next group. Thank you.